Hello students, in this video we'll discuss about register allocation and assignment. So in the last video we have discussed about people optimization, that optimizing a particular basic block by keeping a window on the whole code. So now if after the target code generation, then finding the minimum or optimal number of registers are very important. Why? Because the registers are existed in less in count. Why means they are costlier, but still why we are using it, because they are fast accessing devices. So based on this, finding the minimum number of registers are very important. So to make our system is fast. So to find the minimum number of registers to a particular code, so here we are going to use some strategies. One is global register allocation and another one is usage count. Third one, register assignment for the outer loops, and the register allocation by the graph coloring. See here, so first we'll go with the global register allocation. See, what does it mean by local first? See, if you are having a basic block, then we have to find the live variables of every basic block. Then we have to allocate the registers. For example, in this variable, assume that A, B, C, D are live. Then we have to allocate 4 registers here. We don't know whether they are going to be used outside of that block or not. We don't know about it, but we have already used this. And once this block is over, we will release that memory. But what if we'll use it in another? Again, there is too many load and instructions. So to overcome that, we use the global live variables, where which variables, instead of their liveliness, we'll use some global liveness, or the frequently used variables are going to be assigned separate registers, so that irrespective of the live in a particular block, some registers are fixed, some variables like frequently used variables. And sometimes we are going to have some fixed variables to hold the most active variables in the inner loop. Right, the outer loop, for every iteration of outer loop, the inner loop will be executed for 100 times, right? What if the first iteration of inner loop is terminated? Generally all the registers will be released. But again, if there are some variables which are going to be active inside the inner loop, so instead of reallocating and again doing it, then we can fix it, right? So to do that task, we have some options here. First one, keep values of variables used in loops inside the register. If you are using some variables in the loops, better to keep them inside the registers for throughout the program. And sometimes we can use the graph coloring approach for the more globally allocation. So what does it mean by graph coloring? That we'll discuss, right? So this graph coloring algorithm was developed by Kempes, right, in 1879 for finding the K coloring of a graph. Assume that K equivalent to 3. For example, if you are having a graph like this, okay, we are having it. So we are having the variables. Then how many registers or how many colors required to graph this? Paint this. Means what is the property of graph coloring? No two adjacent nodes are having the same color. So for example, if you are saying that A, B, C, D, then what you are supposed to do? You have to allocate one color here. So definitely this color will not be used for C and B because they are adjacent. We can use the same thing for the D because A and D are not adjacent nodes. We can use it. Then let me use another color like red to here. Okay. So then I cannot use this red to B and I cannot use this color to B. Then definitely I need one more color, right? So I must need another color to color this B. So how many colors are required here? 3 colors. So this is very easy. As we are a human being, we can do like this. But what if it is given to a computer? Then we have a algorithm to do it. What is that? First assume that if you feel that 3 colors are enough, first you have to assume it. Yes, for this graph 3 colors are enough. Then what you are supposed to do? You have to remove all the edges which is having 3 minus 1, all the nodes, sorry, we have to remove all the nodes which is having 3 minus 1 edges, and we have to push into the stack. Once we have pushed all such nodes, if you can't find that, you have assumed 3 colors, But if you can't find a node which is having 3 minus 1 edges, 2 edges, then we can say that 3 colors are not enough. Then you can change your assumption to 4, right? So for example, I feel that here 2 colors are enough. Assume that k equivalent to 2. So does any node is having less than 2 and means 1 edge here? No. So definitely 2 colors are not enough. Then you can change it to 3. Then you can do that. How it is going to be worked out? So one, you have to take it from the stack, then we have to assign a color, and you have to do the repeating, right? Repetition of the step 2. First one, push it, then color it. That I'll explain with a graph which is available here. So I'm assuming that first k equivalent to 2, right? Sir, how you know it means? That's what I'm saying. You try it. If you find edges less than 2, well and good. Otherwise, you increase the number to 3. Okay. So as I'm having the highest degree is 3 here, now I'm taking 2. We'll try it. What will be happen? So first what you have to do, you have to push them into the stack. Which we have to push? Any node. For example, if you are having any node which is having less than 2 edges, that you can push it. I cannot push the A, cannot push the B, but I can push D, E, C. So I'll go with this E. Then after removal of E, right, assume that the E is removed. Then the B is having only 2 edges and D is having only no 1 edge. Then I can go for D. You can go for any. So after removing these two nodes D and E, now B is having 1 edge, C is having 1 edge, but A is having 2. So I'll push B. Then after removing B and all of its edges, then A is having 1 edge and C is having 1 edge. I'll go with the C first, then A next. So like that you have to push it. If you can't find any node which is less than 2 edges, then you increase the k value to 3. So once it is done, then what you are supposed to do, construct the same graph by popping out the nodes from the stack. Let me go with the A first. Okay, so then I'm taking A as a green color. Then I popped out. What is the next node to be popped out? C. Then do one thing. So we can pop out the C, right? And you can push here. I'm using the black color and we can establish a link. Okay. So two adjacent nodes are having the different color. Then I can perform the B pop. Then you can insert here and establish a link to A. As I'm not having the adjacent two black nodes. Black is adjacent to green, green is adjacent to black, but B, C are not adjacent as they are having same color, no problem. So then you can pop out the D, but you cannot use the B color, right? Then I'll change it to green because we have already used the green, right? Then I can go for the green. So D, right? Repeat it. Then I'll go for the, after D, I can even go for the E by using the same color. See, I've done it. No two adjacent. If you can't do it, that means we have to increase the register. So like that, once you represent it, then the how many number of colors are required, those many number of registers. Then the next one is usage count. So here we have to divide the code into blocks and we have to find the use of a variable in each and every block. Okay, then if X is, for that we use the liveness of a variable that we'll discuss how to find the liveness in the next slide. Okay, so what is mean by first liveness? Okay, what is the definition? Example we'll discuss in next slide. So a variable is said to be live at any point in the program. The variable value should be used in the future. If not, that is dead variable. For example, if I take A equivalent to 10 plus B, how can I say that A is live here? Somewhere later in the program, this A value must be used. If not, then I can say that A is dead. So how should I know that whether it is used or not? First, you have to find the use of a variable by using this formula. Use of x comma b plus 2 into liveness. So we have to assign the 2 because we are going to enter into a block and exit from the block. There is a reason you have to take these 2 units of saving. Then we can take that whether it is live or not in that particular block. Okay. So then the number of times x is used in B prior to any definition of x means before this block how many times it is used, that is nothing but the usage. And liveness means if it is live in that block, then we can say that 1, otherwise 0. Okay, I'll explain this liveness with a simple flow chart. Let me go with this. See guys, liveness is a bottom up approach, right? It is a bottom up approach. You have to go from bottom to top and assume that some variables are live after a particular block. So they have given that B, C, D, E, F are live before coming to prior to this block. They are saying it. Now see what is the live variables here? B, C, D, E, F. Okay. So then you have to take every variable from year to year if it is not used as a left hand side. Why? Because see B is used somewhere else, right? So B is somewhere else. Now we are freshly defining the B here. So whatever the definition for before this, that is going to be dead here. So we are reassigning it. So then what we can say that B, C, D, E, F are the live variables here. You have to take every variable from year to year if it is not used in the right hand side, sorry, left hand side. Yes, B is used, so don't take it. C is not used, take it. D is not used, take it. E and F, and whatever you have used here must be here. So D and C already there, no problem. Then take this live as year and year, B, C, D, E, F, and B, C, C, D, E, F here. So what are the live variables here? Same. You have to bring everything from year to year if it is not used here. So C is not used, take it. D is not used here, take it. E is not used here, take it. But F is used here, that's why I didn't take it. And whatever we have used here must be here, right hand side. A is not here, that's why I am taking it. Then same way you can do here. From here we got the BDEF. From here I got the CDEF. Then union is BCDEF. Do it the same thing, right? So you have to take the live variables here. B is not used, take it. C is not used, take it. D is not used, take it. But E is used here, don't take it. And F is not used here. So same way A, then we have to take A. Same B is used here, don't take it. C is not used here, take it. D is not used here, take it. F is not used here, take it. A is not used here, take it. And whatever you are having on the right hand side must be here. So we use the left hand side variable to remove it. Then perform the union of ACDE and ACDF to find the live variables for this block. ACDEF. Then do the same thing, guys. A is not here, take it. After every statement, C is not here, take it. Only E should not be taken, F. Then same way after this definition, D should not be taken. Then you can take the remaining all. A, C, F. And of course, B is on right hand side, that we have to take it. Then same way A is here, don't take it. Then remaining all we can take, like C, D, F. And we are having B, that's why I take it. So this is how you are going to find the liveness of a variable. So these are the variables before it, and these are the live variables after that. So then if A is E is here, yes, then it is not a dead. So D is here, yes, A is here. So F is here. Something which is not here, then that is a dead. All are here, no problem. See, B is here, no problem. So this is how we have to find the live variables. And how many maximum variables are live at any point of our program? 5. So I can say that 5 registers are enough to execute this code. So that's how it is going to perform. Then the next one, register assignment for outer loops. See, if the outer loop contains some inner loop like L2, like we are having L1 and inside we are having a loop called L2, right? So the names allocated registers in L2 need not be allocated registers in L1. So whatever you have used here, don't allocate for it because they may be frequently used. And for example, X is used in L2 but not in L1. So we must load X on entrance to L2. Means we have to allocate a register for this X, right? So and whenever the inner loop is exit, we can remove it or we can deallocate that. Okay. So then the graph coloring we have discussed. For example, we have taken here like this. We have already discussed about it. We need 3 colors, but assume that the user is allocated only 2, or the user is saying that we are having only 2 registers. Then what we can do, you can store the one node completely in the main memory. For example, this, and I'm storing in the main memory. So the bringing or storing a variable and all its liveness to a memory is called spill. So that how many colors are required, use one color here, then 2 color here, then again you can use the same one color. We can use the same color, so 2. That's it. Don't consider the other one. Next we'll discuss about principal sources of